This video contains the notes for section 10.7, which is about Taylor and Maclaurin polynomials. And just a little bit of historical background. Brooke Taylor was an English mathematician, and Colin Maclaurin was a Scottish mathematician. So for all of those theorems and all the great mathematics that was done by the continental mathematicians, the continent being the European continent, here we have two from the British Isles. And if you are like Eddie Leland and you find your ancestry there, then here is something that you can be proud of. Taylor and Maclaurin. All right, so basically what these are, and they're basically the same thing. I'll explain what a Maclaurin polynomial is. Maclaurin is just a special case of a Taylor polynomial, but there are so few British and Scottish folks that they decided to give them both names, get a couple, and one extra name in there. Taylor polynomial is basically not a tangent line approximation, but an approximation with some polynomial of whatever degree that you want, however much trouble you care to go to. So let's start by just thinking about what a tangent line approximation looks like. So let's say we have some function f of x, and we want a tangent line at x equals, at some point we'll call it x sub 0, right? A tangent line there. Well, what we need is we need the point. We need it to go through the point that I'm just going to call x sub 0, comma, f of x sub 0, right? It needs to go through that point, and it needs to have a slope of f prime of x sub 0, because the derivative, after all, just gives us the slope. And then in point slope form, we could write it as y minus y is equal to the slope f prime of x sub 0 times x minus x. And then if we wanted to solve for y, we could write it like this. Y is equal to f of x sub 0 plus f prime of x sub 0 times x minus x sub 0. That's a tangent line, right? In point slope form with this moved to the other side. Now let's say we wanted to find instead of a tangent line, let's say we wanted to find a fourth degree polynomial. And the more curvy we can make our polynomial, the better we can get it to fit our original function. So let's find a fourth degree polynomial approximation for f of x. All right, well, it starts the very same way that we do a tangent line. We know that it has to go through x sub 0, comma, f of x sub 0. We know that it has to have a slope, or first derivative. I'm going to call it the first derivative here. We called it the slope there, same thing. Has to be f prime of x sub 0. Second derivative, or its concavity, has to be the same as the second derivative of our function at that point. The third derivative, you can see where this is going, right? The third derivative has to be equal to the third derivative of our function, and let's squeeze in over here, and the fourth derivative has to be equal to the fourth derivative. And when we get into like too many of these little marks, we sometimes just put in parentheses a little 4 up there, so as not to confuse with raised to the 4th power. That means a 4th derivative. I believe our book does that too, at x sub 0. So if we want a 4th degree polynomial, it has to go through the right point, and it has to have the right first 4 derivatives. So it would have to look like this. Now, for reasons that I hope are fairly clear, it's going to start like, it's going to look like a tangent line to start with. Actually, let me start like this. We know that it's going to be a 4th degree polynomial, so that will be some number plus bx plus cx squared plus dx cubed plus e, not to be confused with Euler's constant. That's just the letter e because I'm going A, B, C, D, E, right? Not 2.71828, etc. It's just the letter e. Okay, we know that it needs to look like this, okay? And to make matters a little bit easier for us, since we want it to go through this point x sub 0, it's going to be a lot easier if instead of doing this, we write it like y equals a plus b times x minus x sub 0. This is so that when we plug x sub 0 in, this is going to disappear to 0. And you can think about this for a minute and try to convince yourself that this, of course, will be a 4th degree polynomial, right? Because the highest power of x will be x cubed here, and finally, in our last term, the highest power of x will be x to the 4th. So we're going to get rid of this. We could use this in the special case where our point was at 0 something, right? Then it would look like this. But more generically, we're going to make it look like this. Okay? Now let's find the derivatives of this. Okay? The first derivative of this function would be b. If you multiply this out, this is just going to be b times x, and the rest is just going to be a constant, right? Plus, or you could think about the chain rule there, how that would work. Basically, just the derivative of what's inside is 1, so nothing happens. And then here, we get 2c times x minus x sub 0, right? The 2 comes out to the front, exponent drops by 1, and then 3d times x minus x sub 0 squared plus 4e times x minus x sub 0 to the 3rd, right? That's the second derivative. Well, what's the second derivative? The first derivative. What's the first derivative when we plug in x sub 0? Now you can see the first derivative is going to be, when I plug x sub 0 into all these, they're just going to turn into 0. So the first derivative is just going to be b. That was the great advantage of writing it like this. So all these terms will disappear. So y prime of x sub 0 is just equal to b. Okay? And I'm going to write that as, let's write it as f prime of x sub 0. Right? That first derivative is just b. Second derivative is equal to, that goes away, this turns into 2c plus 3 times 2 times d. You're saying, why didn't you write 6 there? Because I want to see those numbers. Times x minus x sub 0 to the first power. The derivative of this will be 4 times 3 times x minus x sub 0 to the second power. And when I find my second derivative, when I plug in x sub 0, that goes away and that goes away, and I just get 2c So that means the c that I'm looking for my polynomial is equal to the second derivative at x sub 0 over 2. Right? Sorry, that looks like a negative sign there. It's not. All right. Third derivative is equal to, that goes away, it's just a constant. 3 times 2, it's almost like a 1 comes out there if you want. Write it like that. There's x, that's gone now, right? This is just a constant. So 3 times 2 times 1 times d plus 4 times 3 times the 2 comes out now, and x minus x sub 0. So the third derivative at x sub 0 is equal to 3 times 2 times 1 times d, and 3 times 2 times 1 is 3 factorial times d. So that means that the d I'm looking for, solving this equation for d, it's the third derivative at x sub 0, sorry, I don't know what that 0 is doing up there, x sub 0 divided by 3 factorial. And finally, the fourth derivative would be equal to, this is just a number, so that's gone. It's 4 times 3 times 2 times 1, and that goes away, right? Because that's just x to the first. So my fourth derivative at x sub 0 is equal to 4 factorial times, oh dear, I lost my e somewhere, didn't I? Sorry. There should have been an e there, and an e here, and an e here. Sorry about that. It escaped. So e is going to be equal to, when I solve for e, divide that over there, it's the fourth derivative at x sub 0 over 4 factorial. Okay, so what does that mean? That means my fourth degree polynomial is, let's see if we can write the whole thing. It is y equals, we're just filling in our a, b, c, d, and e into this now. The a, well, that's just a number, right? That's just, sorry, that, oh, I didn't do that, did I? When I plug in x sub 0 to get the point, all those go away. So the first a is actually equal to just the value of the function. You can go through and do that same exercise. You just get a is equal to, I should include that here. Sorry. You're going to find that that's just equal to a. So first, just like in our tangent line, that's just the value of the function. F of x sub 0 plus f prime of x sub 0 times x minus x sub 0. Notice that the first two terms are exactly the same two first terms as the tangent line, plus second derivative x sub 0, and here I got to figure out what's my c now. C is, I got a 2, and notice that 2 is equal to 2 factorial, right? Just 2 times 1 times x minus x sub 0 squared over 2 factorial plus, then the third derivative times x minus x sub 0 cubed over 3 factorial plus the fourth derivative. You can see the pattern here. Once we do this one time, we just need to remember how the pattern works. We'll be all set. There it is. If you want the fourth degree polynomial approximation, we call that the fourth Taylor polynomial. It looks like this. The first two terms, in other words, the first degree, looks just like a tangent line, right? Point-slope form. And then all of the subsequent terms are whatever derivative the term is, so second derivative times x minus x sub 0 squared over 2 factorial. So this is like the 2 term. Second derivative, second power, second factorial. Third derivative, third degree, 3 factorial. Fourth derivative, fourth degree, 4th factorial. And that is it. That's how you find a Taylor polynomial. And before we go on and try a couple examples, just tell you that here's the general recipe. The Taylor polynomial of degree n for f of x will look like this. It'll look like y equals f of x is just, I'm just rewriting what we had there before. This is our general recipe. F prime of x is x minus x sub 0 plus f double prime of x sub 0 times x minus x sub 0 squared over 2 factorial, etc., until you come to the last one, which will be, if we're going to degree n, it'll be the nth derivative at x sub 0 times x minus x sub 0 to the what power? You got it, the n power, over what factorial? You got it, the n factorial. Okay. So you can make a 10th degree polynomial, you make a 617th degree polynomial, you go as far as you want, right? All right. In the special case, if this point is 0, then this looks a little bit simpler, and actually we'll end up doing more of these Maclaurin polynomial. Of degree n for f of x. The Maclaurin just means that the x sub 0, we're doing it at 0. Wouldn't want to say at the origin because we don't know that it goes through the origin. We're doing it like at the y-intercept of the function. That would be y is equal to f of 0, I'm just plugging 0 into all of these for x sub 0, right? Plus f prime of 0 times, notice that these are going to be 0, so that's just x now, plus f double prime of 0 times x squared over 2 factorial plus f triple prime 0 times x cubed over 3 factorial, yada yada yada, until we get to the nth, however far we will want to go, the nth derivative at 0 times x to the n over n factorial. That is it. So let's do some examples. Let's find the second Taylor polynomial. Second Taylor polynomial means second degree at x sub 0, 0 for natural log x for that function. All right. Now, you might have wondered, if you're paying attention here, why didn't I call it a Maclaurin polynomial if it's at 0? Well, a Maclaurin polynomial is a special case of a Taylor polynomial. It's like calling a square a rectangle. I mean, a square is a rectangle after all. It's just a special rectangle. And I'm going to follow the lead of the College Board. They almost never say Maclaurin polynomial. They just call them all Taylor polynomials. And if it happens to be at 0, it just means it's all the easier for us. Okay, so if we're going to do a second degree Taylor polynomial, we need to have up to the we need the function, obviously, and we need the first two derivatives. So what's the derivative of natural log? It's 1 over x. What's the second derivative of natural log? Well, that's x to the minus 1, so it would be minus x to the minus 2, or minus 1 over x squared. Right? And now we're going to need the values for these evaluated at 0. Right? So, oh dear. Here, I'm going to fix this. I made a little mistake here. I gave you one. It's, of course, the natural log function is not defined at 0, so that's silly. The derivative of that would then be that, and then the second derivative would be we'll just put a little x plus 1. Sorry about that, squeezing that in there. So those are the derivatives. So what do I get when I plug 0 in here? I get natural log of 1, which is 0. And then the first derivative would be plugging 0 in here, I get 1. And the second derivative would be plugging 0 in here, I get negative 1. Okay, so now we're just going to follow this recipe. So my second Taylor polynomial is y equals the value of the function, which is just 0. I'll write it here. Of course, you don't have to write the 0. Plus the first derivative times x. The first derivative is 1. Plus the second derivative, which is negative 1, times x squared over 2 factorial. So just simplifying that a little bit, and that's going to be x minus x squared over 2. There you go. That's the second degree Taylor polynomial. And let me grab my calculator just right here and show you what this looks like. What looks like, you say? Well, how does this approximation stack up? How does it compare to the function itself? And is it really better than a tangent line? Well, let's look at the function, the natural log of x plus 1. And I'm going to look at it in the window. Since it's not defined for negative values, let's go 0 to 4, say, and the y scale at negative 5 to 5. See how that looks. And actually, since I did the natural log plus 1, I'm going to go from negative 1 to 4. So you can see it plunging down. It's vertical asymptote, and I'll make this a little bit lower since it wasn't getting up that. All right, there's a pretty good look at it. All right, now, if we had only done the first degree, then I would just get a tangent line, right? If I had only done this. So the tangent line to this thing is here at the origin is y equals x. So let's take a look at that and see what that looks like. Y equals x. There's its tangent line. Great, we've done that before. Okay, now let's make that a little bit better. Minus x squared over 2. Now we have a second degree approximation. There's the original function. And there's the second degree approximation for it. So you can see it does a little bit better than a tangent line. It hugs it a little bit longer in there for a little bit bigger stretch. All right, let's do one more example. This video is getting a little bit too long. Let's try let's find the fifth Taylor polynomial for f of x is equal to sine x at x sub 0 equals 0. Okay, if we need a fifth degree Taylor polynomial, we need the first 5 derivatives of the sine function. Well, that could be a pain, but of course the sine function it's not, because we have the function itself. The first derivative is cosine x. The second derivative is negative sine x. The third derivative is negative cosine x. The fourth derivative is back to sine x again, and the fifth derivative is cosine x again. So that was easy enough. And then plugging 0 into all these, so f of 0 is, the sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is negative 0, or just 0. The third derivative, negative cosine, that's going to be negative 1. The fourth derivative is 0. And the fifth derivative, same as the first, is 1. All right, so let's write it now. So back to our recipe here. My fifth degree polynomial is y is equal to f of 0 plus f prime of 0 times x plus second derivative times x squared over 2 factorial plus the third derivative times x cubed over 3 factorial plus the fourth derivative times x to the fourth over 4 factorial plus the fifth derivative times x to the fifth over 5 factorial. And simplifying that, getting rid of the zeros and the ones and stuff, we get x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. There it is. That's the fifth degree approximation for the sine function, or in other words, the fifth Taylor polynomial. And I'll just really quickly show you what that looks like. Let's go ahead and let me see what mode I'm in. Of course, we need to be in radian mode because we're doing calculus. So I'll put my sine function in, get that out of there, and get a nice window for that. Let's just do zoom trig. That'll be that should be pretty good. That should do it just fine. Okay, then let's graph. What would it have looked like if we just did the tangent line would just be this, y equals x, right? So let's look at that. Here's the first degree approximation, or in other words, the tangent line. Yep, that's a tangent line, all right. Now let's see what the second, there is no second degree approximation, right, because the square term went away. So let's try the third degree. It's x cubed over 3 factorial is 6. See how that looks. There's our original function. Ooh, so it looks like it's pretty good from like, oh, I don't know, about negative pi over 2 to pi over 2. It looks like it's doing a pretty good job. Let's see how much better it gets when we put in plus x to the fifth over 5 factorial is 120. There's our original function. Come on, how cool is that? And if we were willing to do more terms, then we could get it to hug even more. And we'll talk more about that and issues related to convergence and so on in the next section.